In this video, we're going to talk about polynomial regression, about how we can implement that in Python. So first, we need to import some necessary libraries. So before starting, this is a Jupyter notebook, and I am currently using the Jupyter Lab IDE, which can read this kind of notebooks. So let's go to the import. We almost always need pandas and numpy in order to process our data. And then in this case, we're also going to use sklearn in order to fit the linear regression model and to create the polynomial features for the polynomial regression. Then we also need a metric. So this mean squared error value will be a way to evaluate our results. And finally, we're going to use matplotlib to visualize, to make some visualizations. So let's import these libraries and let's increase the font size to make the plots bigger. Okay, so our example is going to consist of a very small data set of only 60 samples. We have taken this data from the Finnish Meteorological Institute, and you can go to its website and download the data for yourself. So if you go to this website, you can see that you can download weather observations or some other kind of observations, and also choose a time period. So it's pretty easy to get this data. In any case, we have already downloaded it, and now we're going to load it into the notebook by using the read CSV function of pandas. So this is the result. So def here is short for data frame, which is what this table is called in pandas. And yeah, so now let's go to the classification, to the regression problem. Before doing that, we always need to define what will be the data point and the feature versus the label. So a data point is always, is in this case, a single row of a data set, and it represents an object with some specific properties. And then the label is the value which we want to be able to predict, and the features are all the dataset columns that are not the target or the label. So if we go on our example, the data point is the specific day and its characteristics, and then we're going to use the maximum temperature as the label, and we're going to consider the day and the minimum temperature as the possible features. So practically our goal is to predict the maximum temperature based on the minimum temperature and the current day. Okay, so first let's keep only the relevant features, columns. And now let's also rename the columns so that it will be easier to access. So yeah, we won't have to write this whole thing every time. So this can happen by changing the columns attribute of the data frame. Okay, now let's drop non-values. In our case, we don't really have any, but this is always a useful step. Okay, so let's visualize the relationship between the features and the label. So as you can see here, the day has a very noisy relationship with the maximum temperature. But on the other hand, we can see a clearly linear relationship between the minimum temperature and the maximum temperature. So, yeah, so we consider this relationship on the right hand to be more informative, because getting the minimum temperature seems to be like a good way to predict the maximum temperature. So since the relationship between the day and the maximum temperature is very noisy, in our case, we're just going to ignore the day feature. And this is actually very useful here because it allows for better visualizations. Because if we only use one feature, then we can make plots like this in the 2D space, which are very intuitive. But if we had more features, then it would get a bit messy. In any case, now we will drop the day column and we will separate the labels from the features. And let's go to linear regression. So linear regression tries to minimize a loss function. The loss function is given by this one. So a value close to 0 means that the hypothesis, which is this h function, is very close to the ground truth y. So our goal is to find this age function that is that given some features will make some prediction that is as close to y as possible. And this hypothesis function is simply a linear combination of the input features. And these w values are the parameters of our model, which we are trying to find. Yeah, so this can be very easily implemented in Python with sklearn. So we are using the linear regression model, and then we simply fit on our data. So let's see what's the mean squared error. So as you can see, the value here is relatively close to zero, which is good. Ideally, we would want this to be uh, zero, because that would mean that our hypothesis function has exactly the same predictions as the ground truth. So our model is practically perfect, but that's not very realistic. In any case, let's see how our model fits the data. So this is the best line that our model could find. And in this case, it's actually pretty good because it does capture the linear relationship between the feature and the label. But what would happen if there wasn't a strictly linear relationship there? So as you can see here, this is another random example. Um, a simple line would not be able to fit this data. We would need some curvature. So for example, here we would need a curvature and then another one here. But a simple line cannot do that. So we can fix it by increasing the degree of our hypothesis function and also include terms such as x squared and x to the power of r, where r is some positive value. So actually, linear regression, which we saw before, is a special case of polynomial regression when r equals 1. Yeah. In any case, to do that, we can use the polynomial features class from sklearn. So what this does is it takes the features and it transforms them to also include these terms, these x squared terms. Yeah. So let's fit different models for different degrees and see how they perform. So as you can see, as we increase the degree, the mean squared error decreases, which, as we said before, is good because we want this value to be as close to zero as possible. But does that really mean that our model is getting better? Well, to do that, it's always very useful to visualize the results. And here we can see how the model acts with lower degrees and with higher degrees. So when the degree is 2, we see that the line fits the data pretty good, but we get a higher mean squared error than when the degree is, for example, 18. So the other lines here are some randomly bad models, just so you can see how a model can fail in polynomial regression. But the best model is this one with the red line. And yeah, we can see some pretty good results with the degrees of 2 and 6, but when we get to degrees of 12 and 18, even though we have better mean squared error values, we can see that the model is very unstable, which is something we don't really want. And this is probably an indicator of overfitting, which means that our model learns the training data very well, and it's not able to generalize on new data. So for example, if we take this a new feature where x equals minus 5.5, so about here, the model with degree 18 would predict a value of around, let's say, 250 of maximum temperature of minus 250, yeah, which is completely non-realistic. And it also does not satisfy our intuition because for a minus 5.5, we would expect the value to be very close to zero maybe, or to one. So as you can see, the model here is not able to predict what will happen with new features.